Hi, everybody. Welcome to the first talk of day 3 of PAW Climate. Here we have one concern and Shabaz Patel. One concern uses machine learning to model the impacts of natural disasters, which improves our ability to plan for and protect against the impacts of climate change, among other disasters. Shabaz leads the data science team at One Concern, and his team is working on modeling the impacts of natural hazards like earthquakes, wind, and floods. And before that, Shabaz has worked on computer vision in the Stanford AI Lab, and later on, he worked on machine learning infrastructure at his company, Datmo, which One Concern later acquired to join forces. Yeah, please, on to you, Shabaz.
Thank you, Eugene. Thank you, everyone, for joining the session. So what I will be covering today is how do we use machine learning in natural disaster modeling. What I will be talking about is starting with what we do at One Concern. So there are two set of main functionalities we really provide. The one is how do you actually think about the impacts of natural disasters N months before the actual event can even occur. The reason why you would want to do that is in order to understand the risk because of natural disasters. You want to assess the risk, you want to mitigate the risk so that you can make sure that you are ready when the actual event can occur. The other functionality or the other product use case which you provide is the event response, and that's around n hours around the event when the actual event can occur. So we provide this for flood and seismic events, and the main fundamental use case for this is to make sure that you can save lives at that particular point by evacuating people based on the data we provide and perform resource allocations at that location based on how the event would be present based on the information we provide on the platform. So in terms of a sentence, what we really do is given a peril, which would be the current ongoing real-time event or a simulated event or a historical event. And this peril could be seismic, flood, wind, and this could also expand to other perils as well. Tell me what is the most vulnerable exposure or the assets which are being exposed to this risk. It would be buildings and locations, the lifelines which supports these buildings, or even the people and communities which are present in these regions. And at the end, you want to make sure that you can act based on the information you provide. It would be for evacuation or resource allocation for event response use case, or you want to reduce and mitigate the risk. So what I would be presenting today is not necessarily an individual work, and it's a work which has been done by the team. And we have deep expertise in different set of regions over here, ranging from structural engineering, seismic and flood modeling, risk modeling, network modeling, seismic modeling, machine learning, and also focusing on the flood modeling as well. We have a deep expertise on flood, and we have a dedicated team focusing just on getting the data sets we need to use for our modeling purposes, and the data scientists can then use them and develop their models based on that. So what I would be focusing on today are basically two items. First thing, starting with what is natural disaster modeling for folks who are not aware of this field before. And the second is where do we really apply machine learning modeling? What's the benefit of using machine learning modeling in the traditional disaster modeling space? So starting with what is natural disaster modeling? So the way how we really think about catastrophe modeling is starting with the natural environment, which represents the region such as soil information or the digital elevation, the way how the city or the region really exists. And then comes the built environment data, which would be the building structure or the levees, which protects the rivers, overflows. And then comes the critical infrastructure and hubs. Critical infrastructure would be something like shelter information, which are used in order to evacuate members from a particular region and make sure they are safe. Hubs would be transportation hubs, such as airports and ports, people and supplier dependencies. If the businesses are dependent on particular suppliers, you want to make sure that you are providing that information so that you can understand how those are getting impacted and how your people are getting impacted as well, so that you can evacuate them at necessary particular resources. And then grid analysis, where you want to understand how the lifelines are getting affected and how your buildings are getting affected because of the availability of lifelines as well. It would be for power, water. You could also expand this to other lifelines as well. And then transit analysis. You want to make sure that your bridges are up and running during an earthquake. How do you know if you're actually coming through the right track or not? So we perform these set of analysis. We want to understand how the risk is being exposed to all these set of infrastructures. The traditional analysis is usually done on the built environment data, such as buildings, and considering the natural environment data. What we do at One Concern is going beyond that, considering these other set of lifelines and the supplier dependencies as well, so that we can capture the risk in a holistic manner. With this information, we call this as the fingerprint, the digital fingerprint of the region or a city, which is now exposed to natural catastrophes. For event response use case, we understand where there could be an earthquake. We use and ingest data sets such as from USGS, which generates the seismic footprint. We ingest those and understand how the impact on the buildings, which would be present in these events. We generate the flood extents on how a particular region would get affected because of flood based on the real-time weather data we have. And now you can also expand this into wildfire. This is something we plan to do in the future, but depending on the risk analysis and the event response product. And finally, you want to use the vulnerability model, understand how the impact and the recovery of each and every asset would be in this region. And now you can understand the risk analysis based on what metrics you really want to capture for understanding the resilience of a particular region. Now, representing all of it in a block diagram, what that really means is you have the data and the exposure layer. The second is the hazard data layer. The third is the impact and recovery models. And then finally, the statistics and the integration for all the set of metrics which we generate. So on the data layer and the exposure layer, we have bridges, substations, roads, power network, buildings, airports, suppliers, ports, and other lifelines as well. And then you have the hazard layer, which would be either seismic flood, windstorm, which these are the three ones which we currently focus on. And now we can also expand this into other perils as well, such as tsunami, winter storm, and wildfire. And now once you have the hazard layer and you have the exposure layer, which is getting impacted because of this impact, we also develop impact and recovery models. So the way how a building gets affected because of an earthquake is very different than how it would get affected because of flood or wind. So we develop individual models which can understand the impact on these buildings. And now once we have an impact on different set of infrastructure, we then integrate or create the final metrics which represents the impact on these particular exposure data sets. So what do we really do with machine learning and AI? Where do we really think it's helpful? So we consider AI as a way on how we can support the existing set of physics-based models and improve the performance of that. It could be either in generating synthetic data sets which are not easily available, or it could be on improving the performance of an existing model by the performance with respect to the metrics which we use, or it could also be in with respect to decreasing the computational cost by usage of surrogate models. And at the end, we use machine learning pipelines which are auditable, version controlled, making sure that the models and the data sets are version controlled so that we can have an auditability on the entire pipeline. Now, applications of machine learning modeling. With this, I'll just start with the flood model, which I described, which is more for the event response use case. And the problem statement which you're trying to solve over here, what you see on the right side is, given a particular region, we want to ingest the new weather data coming in and generate the flood extent and how it would actually evolve with time, so that the emergency responders can take that information and act based off of that in terms of evacuation purposes. And what you have over here on the pipeline side is starting with the data layer, which is again the natural environment data and the built environment data. You ingest the weather data in a real-time manner. You get new data sets, you ingest that. There are three set of models which are being run in parallel. First one is to understand how the rivers would actually flow, how the stream flow would be present based on the new data we have. The second is how the surge height would exist around the region. So if there is a typhoon, we have to capture how the heights would exist around the coastal areas. And the third one is the urban model. We want to understand how a city would get affected because of urban impacts. Now we combine that and understand how which regions would get affected. When we are performing an entire large-scale model, it's important to make sure that we don't run a very high computational intensive model, such as Moe or Schism in multiple regions. We make sure that we understand which regions would get alerted because there's a possibility of flood, and only run the inundation model in those specific regions. Now I'll go into an example on how inundation model would really generate an output slide. So an example over here is for Hagibis event. In 2019 in Japan, there was a typhoon Hagibis, which had affected around Tokyo. And what you see over here is an analysis done on a region called Nagano, which hadn't been impacted. The inputs into this inundation model is storm surge information coming from the coastal model, the riverine stream flow, the urban rainfall runoff information, and then the outputs which we get from the inundation model is the depth of water and the velocity at a particular lat-long location and a temporal horizon, so that every hour you are actually understanding what's the flow of water really looking like at a particular location. Now, this is an image on in Nagano on how it had affected their city. And what you see on the middle is an image which was generated by the government on how the flood extent really looked like at a particular region. And what you see on the right is the predicted flood extent based on the radar data, which is the actual observed precipitation information on the region in the region. So this is how the flood pipeline actually works. But how do we actually use machine learning over here? So there are two ways on how we use machine learning in this particular pipeline. We focus on the riverine model, where we try to improve the performance of the existing riverine model. And the second is on improvement of the data sets which we have. It would be for the built environment data. We want to make sure that we have necessary information required for modeling it for the entire country. So riverine model, the way how we use the model is we use a physics-based model called ListFlood in order to model it for Japan. And we need to train the model using the historical streamflow data and the catchment information, which is in order to represent how the rivers would structure would actually be present in the region. And the input is also the weather data, which is also used in the inference stage. With these three set of information, we actually calibrate this model. In order to calibrate this model in the right way, we use an evolutionary algorithm to make sure that we can calibrate this in an efficient manner. And on the inference stage, we generate the model streamflow, which would be generated by this physics-based model. And one of the projects which we are currently we are doing along with Columbia University is in order to use a machine learning model in order to improve the performance of the streamflow information. So we can use a model such as LSTM and post-process the streamflow so that it can improve the already existing streamflow information. And we use a few specific metrics in this specific field, which allows us to make sure that it captures the right set of metrics. We use a metric called KGE, and we improve that specific metrics to make sure that it appropriately improves the performance of that streamflow information you're measuring. The other set of values which we also use and improve and provide is water level information. So converting the information from stream flow and converting that into water level, we use a simple machine learning model to make sure that we can showcase the water level information so that the users who are the emergency managers who are very much accustomed to understanding from the water level, the height of the water along the rivers and make unnecessary actions based on that. So that's another place where we use machine learning as well. So next is generation of synthetic data sets. One of the biggest challenges which we faced is in getting the levy data sets. For one of the cities in Japan, we worked with the local officials in the city, tried to get the local information on how the levy structures are usually present. And Japan is a very well defended country, and over the last few decades, and we got those data sets, but it was a very slow process. We had to get the data sets after a set of rigorous local interaction, and it took almost around 6 to 8 months to get the data sets for a single city. So we decided that that's not going to be scalable if you want to do it for multiple cities in the country. So we developed a machine learning algorithm using data sets such as OSM, OpenStreetMap, and digital elevation map, and understand how the levees really exist in the particular city. And now that allows us to deploy it in multiple cities in a significant, quicker manner. And we don't have to rely on the cities themselves. If the cities can provide us those data sets, that would definitely improve on the existing set of data sets we have. But we are not completely reliant anymore by using machine learning. So this is again an example where we use OSM data, the DEM, we generate a few set of features, and then we apply a random forest model over here to understand the levy probability, and then create the vector line. The challenge in this project was more around understanding the set of features and feature engineering in this custom manner so that we can generate the features and then apply the algorithm and then generate the levy lines. Then I'll go into the next set of model, which is the seismic machine learning model. And in this example, what we have done is improve the existing performance of the models in this field. Fragility functions is a well-known model which is widely accepted, state of the art. We use the fragility functions as one of the input features into a machine learning model, take in other features as well, such as an earthquake intensity, the shaking which is present at a particular building location in that particular region, and then also the soil characteristic as another feature as well. And then we include those features into our machine learning model. We train our machine learning model using those historical earthquakes. And then it's a classification problem where we try to understand the damage, the probability of a particular damage state. And we understand that for multiple buildings in a particular region and then aggregate it over a particular hexagonal representation. And the challenge in this was the feature engineering, and the second was the making sure that historical earthquakes are not really going to be encompassing all set of features as well. We had to make sure that we can increase the features by generating synthetic data sets, so that even if our models have not seen a earthquake data set in the training data, which has not occurred in the past, that doesn't mean that we should not be training our model, and we have to make sure that the coverage exists even for new set of earthquakes which have never been seen before. So we generated a new set of training data sets so that it can increase the coverage of the models which we have built, and then use that for new earthquakes, and we deployed this into a product. The last one, which I'll go into, is the power outage model. The problem statement over here is in understanding how would power availability get affected in a particular building if there is an earthquake, if there is a flood or a wind event. An example over here, what we are seeing on the left side is an actual data set which is showing the damage to the power network, which was reported after Nisqually earthquake, which had occurred in 2001. And getting this specific set of network data is very difficult. And if you want to do it for large scale modeling for the entire country, and getting such data sets is a big challenge. What we had done in this specific project was synthetically generating the data set for representing the distribution lines of power in the city, and then understand how those can get affected. So we apply impact and recovery models, and in this case, it's only the impact models. The red represents the impact in a specific region, and the blue is representing that there is no impact on those specific region. So there has been a lot of updates on the specific model, but what we are showing over here is how the problem in itself, on how challenging it is to actually get these specific data sets and then apply a system level analysis. So the way how we approach this modeling is starting with network generation. We have a source node, which would be the power substation, and there would be a demand node, which would be the building which is consuming the power. And we try to understand which buildings would have overhead distribution lines and underground distribution lines. That's the first model which we develop. And the second would be in associating power substation to the building nodes, which would be consuming the power. So we developed clusters of different networks, which represents the power substation to the buildings which are consuming the power. And then the next step over here is once we generate the network, this would also have the power poles over here, which is what you see on the dotted lines here. And once you have the network, you understand the disaster severity, you apply the fragility curves, and you have the probability of damage of different components in this network. Now, once you have the probability of damage states in this network, we apply Monte Carlo analysis. We create the multiple samples, which has different states on what is possible. And then we apply connectivity analysis to understand if at all a particular Monte Carlo sample allows us to provide power to a particular building in this, which is consuming power here. Then we aggregate this over all the Monte Carlo samples, and we have probability of power availability at a particular building location. So in this example, what I really wanted to show is the challenges which is present in getting the data sets, where we use network-based algorithms to generate the data sets and then perform network analysis in order to get the impact because of power. Impact to power because of natural catastrophes. Finally, I want to conclude by talking about the availability of the challenges which are faced in the natural catastrophe modeling and the problems we are solving with machine learning modeling here. The first is in order to generate the synthetic data sets, we use machine learning modeling and network modeling approaches to generate the synthetic data sets. The second is in order to improve the model performance, we combine the physics-based model as an intermediate features generator, and then combine that along with the machine learning model to further improve the performance of the existing models. And the third is in order to generate and create the surrogate models so that we can reduce the compute time and the cost due to the models which we have in the physics-based model. And this is basically the conclusion. And let me know if you have any questions.
Yeah, thank you so much, Shabaz. Excellent talk. Yeah, really interesting to see like how you're combining machine learning with domain expertise in disaster modeling here. So there are a couple of questions there. So one is, how could the machine learning open source and research ecosystem help companies like OneConcern? Like, what data sets do you need? What new methods do you need? What libraries? Maybe competitions on Kaggle or something?
Yeah, so the biggest challenge which we have is getting the right set of data sets. Let me go back to the slide here. When you consider the entire chart over here, which represents the development of these impact and recovery models, having the necessary damage data sets is very difficult, which can be used in order to calibrate these specific damage and impact and recovery models. So any data sets which in ecosystem which can be formed in order to help different companies come together, academic institutions come together, which can help create a huge amount of data set which can be used by the entire ecosystem, by industry and academia, and helping each other out in order to develop better models would help the industry as a whole to have a better models which can be used in the industry as well.
Do you know of any initiatives on creating these data sets? Like, is there something that people go and help participate in?
There isn't any right now, but that's something which which requires a huge group of academic institutions to come together along with industry like ours, so that we can make sure that we can support such kind of causes, and we can work with other different companies as well, which can help us support that.
Got it. Makes sense. Yeah, I hope that situation improves.
Yeah.
Another question somebody just submitted a few seconds ago. Do you make models only for bigger cities or also smaller cities, villages, and rural areas?
Yeah, I mean, we definitely generate and create models for all set of cities. There's no restriction for us to generate it. The only biggest challenge is making sure that we have the necessary data sets, and that's why we have those synthetic data sets generation models, so that it can allow us to go into a new city as well, regardless of the size of the city. So the size of the city is not the constraint. Getting the necessary data sets in order to model it is the main constraints, which we make sure that we have it through synthetic models we have.
See, yeah, I guess that's probably also a possible extension of this question. Like, are you trying to maybe also model the impacts on like natural ecosystems without the built environment?
I'm sorry, natural what?
Are you trying to also model the impact of sort of climate damages on the ecosystems that do not involve humans?
Oh, you mean
just ecosystems?
Can you give me an example?
In nature? For example, I don't know, like what might happen to populations of certain species in a forest? Like how is
That's a very good idea. Yeah, so we are actually modeling it for different regions where the decision makers can take actions, and it would be so. For example, when you are modeling it for event response, it would be flood extent in the entire city, and you can also expand this into other regions as well if you want to look into a few specific regions where there are endangered species, and we can understand the impact of flooding in those specific regions, so that the responders can then act and make sure that those endangered species can also be saved over there.
Makes sense. And just one more last question. If you look at the people that are working at OneConcern in machine learning or data roles, like where do they come from and what brought them there?
Yeah, so that's a good question. So let me go back. So the members who are actually working over here at OneConcern, they have deep expertise in their field, which they are coming from. What you see over here, their members are coming from, they have PhDs in their specific field. All of them over here, Chengwei is coming from University of Michigan. He has a PhD from there. Deepak has a PhD from a university in Japan. Iskanwal, Junichi, all of them have PhDs in their specific field. machine learning expertise as well. And risk modelers are coming from industries where, such as like AIR, which is also in this field of developing risk models. And other set of members, which you also see over here, the flood modelers also have PhDs in their specific field. We want to make sure that we have the necessary set of expertise in order to develop these models, which are custom models in this field, which can allow us to build a very well-trusted model, which can allow us to deploy in cities with much more high reliability. So internally at One Concern, we also have developed a model review board to make sure that any model which has been researched, which has been developed, goes through a set of checks and balances to make sure that before it goes finally to the customer, it's getting approved. We also have a technology working group, which has professors from different universities, University of Michigan, Stanford, Virginia Institute of Marine Science, which is also an expert in this field, to make sure that we can get the right feedback into improving our models. And then once we have an approval from the model review board, only then we deploy the models into production and then gets used by the customers.
Got it. Yeah, very interesting. Great to see. I often see people who do research in these domains, like flood modeling or earthquake modeling and so on, and they wonder like, where can we go work? Like, are we bound to work at the university? And the answer is clearly no. Like, there is commercial demand for it.
Definitely.
Yeah. Thank you so much, Shabaz. I'm going to switch to our next speaker, Buffy.